So what we're hoping to cover in this video would be everything within Chapter 10 as far as the new reactions. I'm going to try and cut through them kind of fast, give you the overview, ideas on them, and when we shift to lecture we'll start talking about the details, mechanistic details, what kind of results come out of it, that kind of fun stuff. I have it organized according to what you see there. So at first we'll talk about kind of better leaving groups within the context of oxygen as an element within your structure, and then within that same token, oxygen is a better nucleophile with epoxides, and the oxetanes will kind of leave for you to look at in the textbook, but those are kind of the relevant sections. After that we'll talk about amines, so now shifting to nitrogen and how that can be used for substitution reactions, as well as looking at elimination reactions. And then the very last section that we'll actually devote any time to, which will actually be a sizable portion, is looking at making better nucleophiles through the use of carbon. So how do we make carbon a nucleophile, which is a pretty tricky subject. So those are relevant sections that you should kind of review, and roughly in that order as well. So to start it all off, we need to know something about the reactivity of the OH group. So what we've got here is an alcohol. And what you should be thinking about whenever you look at a structure is what chemistry is available to it. Okay, so to start that off, what we're really referencing is it a nucleophile, electrophile, I'm running out of space, electrophile, Bronsted acid, or Bronsted base. Okay. So every time you look at a structure, these are the things that should be clicking through your head. That position acts as this, that position can act as this. Because ultimately, that will be true depending on what reagents you're adding into this. So, when we go through and look at the reactivity of the OH group, what you might see is that we have a nucleophile in the presence of that oxygen. That oxygen has lone pair electrons, it can act as a nucleophile. Which means it could also act as a Bronsted base. We do have some acidity in that hydrogen, but it's relatively weak, but we do have some acidity out there. And then we also have some electrophilicity in the carbon. Okay, so most of the sections that we're looking at within this chapter are now bouncing around those 3 points about the oxygen, saying, okay, how do those things affect? So once we're now looking at these, we can now evaluate what can we do to enhance or stifle this chemistry. So if we were going to look at that electrophile, for that to be a useful electrophile, that oxygen needs to then be a good leaving group. Well, it's not a good leaving group right now. You'd have OH minus. Okay, so to get that to act as a good electrophile, I need to fix the leaving group. And that's partly what this chapter is. What are those fixes? To look at the nucleophilicity. Okay, well, it could act as a nucleophile because of those lone pairs, but it's a relatively weak nucleophile. Okay? How can I make it stronger? What is the fix for that nucleophilicity? Well, that fix is actually going to tie back to that hydrogen. We could go through and react it with an acid, with a base, to remove that hydrogen, and we now have a stronger nucleophile. So we've identified the rough chemistry. Now it's time to look at the details of this and see what we can do with it. So in the first thing, we want to try and activate our leaving group. So really what we're addressing is I want that carbon to react as an electrophile, which means, sorry about that weird pause, this group above must act as a leaving group. For it to do that, it needs to not be OH minus. Okay? So how do we fix that? Well, one thing that might stand out as obvious based on the reagents I've got shown there is we could react our alcohol first with an acid. Okay? And it's going to have to be a relatively strong one because the oxygen is only sort of basic. So we can react it with a strong acid, which then goes ahead and protonates that position. Now I have a really good leaving group. Once I have that good leaving group and my reasonable electrophile, now things can start to get interesting, and we have to kind of think about what's going to happen in the next sequence of steps, mechanistically. So before we push into that, we now have to decide what is A minus. Okay? Because depending on what that is, we may get a different result. So the common ones that you'll end up, whoops, we don't even need to look at the list quite yet. In this upper case, what we're saying is that A minus is a reasonable nucleophile, in fact a pretty strong one, hence it immediately attacked in that upper case, meaning that we had an SN2 type situation. Backside attack and kick that out. Okay. In that lower case, we're running an SN1 or E1 type reaction because we're forming the carbocation, and we're saying the leaving group just left on its own. Okay. Under both those circumstances, we can then run into the case where now A minus can come in and react with that cation, or we can do the elimination reaction, depending again on what we're working with. You'll notice that I did not show any result for the E2. Important question. We'll ask that when we get into class. Why is the E2 not shown under these circumstances? After that, what is A minus? Well, A minus could be iodine. Okay? Really strong nucleophile because of its large size and its negative characteristics. So iodine could be used here. And then I'd also be having HI instead of HA, and HI being a strong acid, this works out. That could also be bromide. Bromide works equally well. It could be chloride and sulfate. Chloride hits a little bit of a question mark. Okay? And the issue with chloride is not so much that it's not a strong acid. It is a strong acid. However, chloride is a weaker nucleophile than the bromide and the iodide. Okay. So what that means is that it doesn't quite work as fast or as efficiently if we used HI or HBr. So we might want to throw something in there to help speed that along. The last reagent that's kind of interesting there is an even weaker nucleophile, sulfate. Okay, it is so weak that we would actually say it's not a nucleophile. Okay, well, if it's not a nucleophile, we can't do the substitution. So what's happening typically when we add sulfuric acid? Well, we end up seeing the elimination reaction. So that is a very common reagent to see pop up. It's known as a dehydrating agent because what we have done when we move from point A, our alcohol, all the way to point B, our alkene, the biggest change is that we lost water in the course of that reaction. Okay, so those are your primary reagents, HI, HBr, HCl, H2SO4. Okay, and they go through these kind of various paths, and you kind of have to watch out for those. So before we take a look at kind of further interesting features of this, let's go back to that HCl. And actually, before we even do that, the primary mechanism in almost all of these is pushing an SN1. Really, the only way we get into the SN2 has to do with our substrate. If our carbon here is a primary carbon, then we can push the SN2. If it is secondary, put in another carbon here, we start pushing SN1. If it's tertiary, we're going that SN1 route. Okay, which is going to be an important question when we get into lab, or sorry, into lecture, because I'll bring in some reactions and you have to think about why we're getting the different results we might get. With the HCl, what we end up adding is a catalyst. The zinc chloride acts as a Lewis acid catalyst. Okay, so if you remember your definitions of your Lewis acids, they accept electrons. So in the very first step of our reaction, the oxygen donates its electrons to the zinc, can kick out a chloride, and we form now our much better leaving group. Okay. This is a significantly better leaving group, which can then account for the weakness of the chloride nucleophile to go through and produce our final product. Again, typically we run through an SN1 mechanism, so we would see the leaving group leave first, and then we would have our carbocation that the chloride could then react with to get us our final product. Okay? The reason that this reaction gets named as opposed to just listing the reagents is because this sequence or combination of reagents was used as a classification test in the old days, which we will probably use in lab as well. What it helps you classify is based on the speed of the reaction, or the speed of a result. In the course of this reaction, you end up converting your alcohol over to an alkyl halide, or an alkyl chloride. The solubility of that compound is so low in comparison to your starting alcohol, which is relatively high, that once you've mixed these reagents, if you see this kind of turbidity or a slight powdery, clear, messy solution, that means that what you started with was a tertiary alcohol. Okay? The faster, or started with an alcohol, the faster the reaction occurs, the more likely you form a stable intermediate, which means you had a tertiary alcohol as opposed to, say, a secondary or a primary. While the primary still works, it works at an incredibly slow rate because our chloride isn't the greatest nucleophile and we can't form the carbocation right away. That means if we have the primary alcohol, we get a very slow reaction. It takes upwards of 5-10 minutes. So for our classification test, that pretty much tells us that we have a different alcohol. After that, we now move into some of the interesting chemistries on activating these. So before we even do that, when we look at these reagents, what you should be thinking about are what might be complications within these. Remember, they are largely driven based on an SN1 mechanism. So think about stereochemistry and why that might be relevant for synthesis. Our sulfur, I don't know why I'm calling it sulfur dichloride, it's thionyl chloride. This is a neat little reagent, and depending on what conditions we put it in, we can get different results coming out of it. The be-all, end-all out of this is that when we mix these two reagents together, we end up with the substitution reaction. Okay? And we can convert our alcohol to our chloride. Why is that relevant? Well, an alcohol had all this other chemistry. We had the acid, the base chemistry. Our halides have only one chemistry. They can only go through the substitution eliminations. They really have very minimal other chemistries. So if I have an alcohol, I may want to convert that down to a halide so that I can target very particular chemistry and not have to worry about the alcohol getting in the way. So it's kind of neat to go through and do that. So in this process, what is going on? Well, the very first thing to do would be to address our thionyl chloride as what is particularly interesting about it. What you should hopefully notice is that there are 3 very electronegative elements attached to that sulfur. That makes that sulfur incredibly electrophilic. So electrophilic that our oxygen can share electrons with the sulfur. This ultimately, officially, breaks the pi bond with that oxygen, because that is the highest energy electrons. And if we drew out our result, we'd have our single bond oxygen with the negative charge, another chlorine here, hydrogen here, positive here. Those electrons on our negatively charged oxygen actually go back in to form the pi bond, and that's when we kick out the chloride as a good leaving group. Okay? Because we can now start to be lazy with our mechanisms, one of the things that you may see would be the electrons come out, attack the sulfur, the electrons go to the oxygen, the electrons go back to form the pi bond, and the electrons kick out the chloride. So what we've done is kind of condensed that big long mechanism that we just drew into one big step, which can get us to that next part. Okay? Here's where an interesting feature pops up. You'll notice that I also included this structure. This is known as pyridine, also abbreviated PYR. It is mildly nucleophilic, particularly when we're in a solution that has such a good electrophile as the sulfur. And what it will do is actually run the substitution reaction and sub out for that other chloride. Okay? And that becomes important when we move into the next step, and I unfortunately did not carry the chloride or that pyridine through. When we go through and get rid of that last hydrogen, we now have chloride floating around, and we now also have this pretty fantastic leaving group. But because we have that big old bulky nasty pyridine molecule up top, the chloride can only really come in from the backside of that bond. What does that mean? That means we get a backside attack. This is running an SN2 mechanism. What does that mean for stereochemistry? Okay, so we get some cool things happening there, and we can force one product as opposed to two. So synthetically, this is a pretty sweet deal. Whoops, wrong button. Let me try that again. Another cool feature of this reaction is that when we actually do that arrow pushing, electrons come in, kick out the oxygen, we can kick out that chloride, and what we end up forming is SO2. SO2 is a gas. Okay? One of the reasons why thionyl chloride stinks so much is actually because of the sulfur dioxide gas. SO2 is or thionyl chloride is so reactive that it reacts with water in the atmosphere to form sulfur dioxide. That sulfur dioxide is what we're smelling. Bit of an unfortunate thing to deal with. Don't worry, I don't make you guys work with it, at least yet. So, some kind of cool, interesting chemistry that comes out of this. This works on all OH functionalities. You may be like, well, why is that relevant? Alcohols have OHs. Well, yes, but so do other functional groups. Think on that one for a second. It will convert those OHs over to chlorides as well. The other thing that's interesting is that if we change the conditions, so what I'm showing down there is now an abbreviated mechanism, and if we take a look at it, what is our primary difference between the product shown in the bottom and the product shown up top? Hopefully you can kind of see that in the red product, I'm showing the chloride came in from the top. In the blue product, the chloride came in from the bottom. Okay? So blue generated inversion of stereochemistry, and red, we have retention. It stayed the same. That difference all centers on that magic molecule of pyridine. Under the second condition, there is no pyridine. If you do not see pyridine, you will get retention of stereochemistry. If pyridine is present, you get inversion of stereochemistry. And remember, that's coming from that last transition state, or that last reagent, which is supposed to be a hexane, sterically blocking and preventing the chloride from getting in. When we get rid of the pyridine, there's now nothing blocking it. Okay, that's a relatively small molecule there, and so the chloride can immediately come in, do the substitution, kick out the leaving group, and we no longer have to worry about an inversion of stereochemistry. So kind of cool. So watch out for that PYR, that PYR down there, or that pyridine molecule showing up. Okay? Those are your big key-offs on dealing with what happens with your thionyl chloride. After that, we can move to phosphorus tribromide, or ultimately, or even phosphorus trichloride. Both of these will end up doing very similar things, same ultimate mechanism. Okay? Kind of interchangeable as far as the mechanism goes. Just like with the sulfur or the thionyl chloride, phosphorus is an equally large atom to sulfur, and it is also equally substituted by some really electronegative elements. this starts to make that phosphorus relatively electrophilic. That then means our oxygen, just like with our thionyl chloride, can attack our phosphorus, kick out a leaving group, and we can end up forming a very similar intermediate as we did with the thionyl chloride. This, again, with our bromide, can now come in, backside attack, and kick out our good leaving group, and we end up with our product. The big result here, this is also SN2 all the way. You get inversion of stereochemistry. So if you think stereochemistry is involved, watch out for it when dealing with these reagents. So type of reaction, substitution, mechanism, SN2. Okay? So whenever we say SN2, you should immediately be thinking stereochemistry. Watch out for it. Okay? Inversion. We say SN1, loss of stereochemistry. Okay? Mixture of products. And just like with our thionyl chloride, the phosphorus tribromide and the phosphorus trichloride will work with carboxylic acids. So it will substitute the OH of a carboxylic acid with a halide. Kind of a neat chemistry. This last one isn't directly mentioned in the textbook, at least within this section, but it's kind of relevant because it's still looking at making good leaving groups. You may see reference to this thing as a TS or a tosyl. The TS in tosyl is that piece right there. Okay? It shows up fairly frequently in a variety of forms, and in fact it shows up as two forms. Call that 1, and we'll call that 2. So what we're saying in that statement is that in 1, if the squiggle is OH, then what does the species act as? So let's convert that now to an OH. What does this species now act as? Well, if we look really carefully, you remember something about Lewis structures, it should start to look an awful lot like that species, which may still be a bit of a challenge to see, so let's rearrange those letters. It's a strong acid. We're looking at sulfuric acid. Okay? So our tosylate, or our toluene sulfonic acid, is a strong acid. So if our squiggle is an OH, we have an acid. If, on the other hand, our squiggle is now a chloride, we take a look at that sulfur, we have 1, 2, 3 very electronegative elements. That sulfur is now a pretty sweet electrophile. We can use that chemistry because our oxygen can now donate electron density into that sulfur, kicking out our chloride, and I didn't actually draw it all the way out, but through a few mechanistic steps, which you should be able to come up with, feel free to ask me about it if you don't, you should be able to end up with that structure. You'll notice that we do not change anything with stereochemistry when putting on the tosyl group. Big question comes down to why. Why does the stereochemistry not change? Well, what atoms are involved in the chemistry? Are either of those atoms stereocenters? No, which means our stereochemistry is maintained, or our relative arrangement of those atoms is maintained. Reactivity of the OH group yet again. Remember, our oxygen could act as a nucleophile, and we also have that electrophilic characteristics of that leaving group. Okay? So we can then push this into ether synthesis. So we've got two options. We can make a good leaving group, or we could make a good nucleophile. To make a good leaving group, we could go through and just add a really strong acid, say H+. That protonates, and I now have a really good leaving group. If I'm still in that alcoholic solution, and this is the next challenge, you need to remember that what we have now is tons of these molecules floating around. It's not just one, there's tons of them. I can have a second molecule come in and attack, kick out the leaving group, and I would end up with If we just kind of simplify, oh man, this is ugly. We could potentially end up with the ether that I think I just drew there. Something doesn't look, no, that's right. Okay. So what we've done in that result, again, beginning to end, what we removed was a hydrogen and an oxygen. So we did a dehydration. Okay, so we can make the ether by making a good leaving group and have another alcohol come in and attack and form our ether. The other option is to go through and make a good nucleophile. This synthesis was thought up by Williamson, and it's referred to as the Williamson ether synthesis. So if we still look at that alcohol, how can I possibly make a better nucleophile? Well, where's the nucleophile? The nucleophile is that oxygen with the lone pairs. For it to become a strong nucleophile, I need to get it a negative charge, which means that species needs to donate hydrogen to something. Okay, well, a species that donates hydrogen is also known as an acid, which means I need to react it with a base. So if I add any strong base, that can then change through reaction 1 my species to instead become this guy. Now that it is negatively charged, I can react that with a standard electrophile, and I can form my second product, or my final product. In theory, yes, there are complications to this, of my ether. Okay? Depending on what base you're using to generate your nucleophile, and depending on the characteristics of your electrophile, you may or may not succeed in making your targeted ether. So you have to be very careful and decide what's the mechanism. In this case, we want SN2, but it could also do E2 because that guy is also a base. So you have to be thinking about the mechanism to decide how to sequence and put together to synthesize your ether. It's a little bit trickier. We can push this even further and put both the halide and the alcohol in the exact same functional, or in the exact same compound. In the extreme case, we use only 2 carbons to attach those. When we add the strong base, our alcohol becomes negatively charged. That negative charge can then come in, attack, and kick out the bromide. The result being, hopefully you recognize that, as an epoxide. Okay? Think about the stereochemistry of that and how that reaction must be aligned to allow for this to occur. Because I will throw a curveball on you on the synthesis of the epoxide with stereochemistry included in it. Right? That will show up in class and potentially the exam. You'll notice that in this case I went through and added 2 more carbons. I would draw those 2 more carbons in. Well, I will draw them in right now, and they will delete very quickly here. I added that information because we've got a lot of extra stuff going on in box A and box B. What about box, let's call it 2? Right, well, what 2 is looking at is saying, hey, is there another way to make an epoxide? Hopefully you all remember, because we briefly talked about it, that we can make epoxides using MCPBA and an alkene. Okay, so we've got 2 ways to make these epoxides. Now that we have an epoxide, we still have some information to evaluate here. We can look at that oxygen still and say, hey, that's a leaving group, potentially. And I can also potentially make it a better leaving group by, say, adding an acid, so that I have an even better leaving group. you'll notice that there are two boxes underneath here. That's because one of those boxes says we force the oxygen off even as a bad leaving group, and the other box is making it a better leaving group before we force it off. Okay? And so if we... What? Oh, well, sorry, I thought the results were going to pop up. We'll see the results here. So if we go through under basic or neutral conditions, so this means I am not adding acid. All that you see noted, or all you should see added here, would be the nucleophile. Okay? You'll notice I also have two drawings. Those two drawings represent one and the same compound. The subtle difference is how we are looking at the molecule. In this first example, the epoxide ring is in the plane of the paper that we're working on. That was kind of poorly drawn. It's in the plane of our papers, wherever we're writing. In the second example, the oxygen is actually perpendicular to the plane. So if we drew this out as a plane, the oxygen is somewhere up here, and this is where we would now be looking at it from. Okay, yes, that's an eyeball. It is important to evaluate where those bonds are located because that's going to help you understand what happens to the stereochemistry when you run the reaction. Back to running the reaction. We now have a nucleophile and a strong nucleophile. We also have a pretty crappy leaving group. So this reaction is not going to be easy to run. It's going to need to force it as best as possible. So this nucleophile is then going to come up and it has two options. There are two positions that have leaving groups. We have position A, which we'll call red, and we have position B, which we'll call, or position blue, which we'll call B. Deciding which of those two positions comes out of looking at the leaving group and looking at the nucleophile. Strong nucleophile pushes SN2 dynamics all the way through. Okay? SN2 says where or runs with which substrate, the more substituted or the less substituted. Hopefully you nail that down as it working with the less substituted with a strong nucleophile. The next part of this is that we have a horrible leaving group, meaning it cannot leave on its own. That's also going to want to then push for it being the most accessible location for the nucleophile. We really get two check marks for our nucleophile attacking position B, not position A. The result, assuming I drew everything correctly, is then the nucleophile comes in from the back side of the bond. We kick that leaving group out, and with a second step of a workup with acid, we can end up putting the hydrogen back onto our alcohol, and we've got our final products. Again, be very careful with your stereochemistry and how those things are arranged. You'll notice the wedges and dashes are kind of shifted around. Okay? They are shifted around because they are coming from the viewpoint of the structure above. Okay? So, nucleophile with our epoxides under basic or neutral conditions comes in and attacks the least sterically hindered site of the epoxide. With all that emphasis, we may think that something else might happen under acidic conditions. And you'll notice the very first thing that happens, well actually even before we do that, are big changes in this reaction. The very first step, I'm adding an acid. Further, we look at the second step. What am I adding? A weak nucleophile, not the negatively charged strong nucleophile of the previous reaction. So, if we work through this, what happens? Our strong acid needs to be neutralized by our base, which in this case will be our oxygen. We can fix our drawing by drawing on our hydrogen now. The oxygen is now positively charged. We do that for both of them. Okay. I now have a very good leaving group, so much so that it's already starting to kind of pull away from the structure. which means I'm starting to form a carbocation. This is the critical difference between the acidic condition and the basic conditions. As it pulls away from the structure, it starts to form a carbocation. Where is the carbocation more stable? At position A or position B? Okay. Position A is more substituted than position B, so A is the more stable carbocation. What does that mean for us? Well, now the nucleophile bides its time, floats through solution because it's all fine and dandy. It's like, that's not very positive, I'll leave that alone. Oh, look at that potential carbocation. That's where it attacks. We draw out the results. Again, you should be able to see the symmetries of what's going on with those products. Note the massive difference in this. The nucleophile is now at the more substituted position as opposed to the least substituted. Huge, drastic difference in results. Right? So watch out for that. Make sure you look at those reagent conditions because that will change your result. Moving on, we've got the reactivity of the amine group with our nitrogen. So we've got our representative amine group here, and we would want to go through and do the same thing that we did with the alcohol. What chemistry is available to the amine? It's primarily the same stuff that we had with our oxygen. We got that nucleophilic and or basic, and actually I'm going to rewrite that here, get some subtlety into this. We've got that nucleophilic nitrogen and or the basic nitrogen. We might try and reference those hydrogens as being acidic, but unfortunately that is not true. Okay? The hydrogens are not particularly acidic when attached to that nitrogen, and it's now looking at that slightly smaller electronegativity difference and the stability and smaller atom than oxygen as far as stabilizing that negative charge. The last thing that we might see would be that we do have the potential for an electrophile at the bottom of that structure. Okay? So what we want to do is think about how we can address and mess with this. This is ultimately the substitution chapter, so heck, why not? Let's start with that nitrogen acting as a nucleophile. So we can run through and do an alkyl halide substitution. Nitrogen is a phenomenal nucleophile, much better than oxygen. This is fantastic. We can go through and do our standard substitution reactions. Okay. Here's the rub though. You see that statement down there? It says take a look at the starting amine and the ending amine. So there's our starting amine, there's our ending amine. What is the difference between those amines? Okay. This is a good time for me to say, well, that silence, that deafening silence, is a good answer. Right? There's a good answer because there is virtually no difference between those amines, which means that primary amine product is just as likely to react with alkyl halide still in solution as the other amine, or as our starting ammonia. What does that mean? As soon as we try and run this reaction, we do not stop at the primary amine. It can continue to react to form the secondary amine, which can continue to react to form the tertiary amine, which can continue to react to form the quaternary amine. Okay, so when we try and do a substitution with an amine, it's a mess. We get very poor yields because we end up forming the primary, secondary, tertiary, and quaternary amines through the whole process. That's a pretty crappy reaction to go through and run. Our yields go through the floor, and then purifying is going to make that even worse. So when we're looking at our substitutions with amines, they do work, they just don't work well. So one of the things you might be saying is then, Mike, why are you telling me about this? This is dumb. You're telling me that this is a horrible reaction, there's no reason that I should run it. Well, could we do anything with a quaternary amine? So let's take a look at our quaternary amine. That is a positively charged nitrogen. Does our nitrogen want to be positive? Think back to our alcohol. Did our alcohol or did our oxygen want to be positive in the alcohol? Does our halogen want to share electrons with the carbon in an alkyl halide, which I thought I'd inserted into this figure, but apparently not. Okay. In all of those cases, what we are noticing is that we have a really good leaving group. Those atoms do not want to hold that positive charge or share those electrons. Our standard amine may be a horrible leaving group, but as soon as we put on a bunch of carbons and make it quaternary, it now becomes a great leaving group. And that's a pretty solid deal. What does that mean for us? We can now potentially go through and use it for substitution. Maybe that gets challenging. But we could also use it for elimination. Okay? So, if we get that quaternary amine, add some base and heat, the two big signs for an elimination, we now can run through our elimination reaction. Phenomenal, super happy, everyone can go home. Not quite. Okay? So, we got the mechanism provided for you in the book, and what you should in theory do is look through that mechanism and decide how many possible products how many elimination products could we have obtained. And hopefully what you do is when you look at that, you should also see that that was a possible product. Okay? And you should think back to your elimination reactions that you learned about in first semester, and you should be thinking, what is odd about this result with our amines that we are generating the product shown in the book, as opposed to the other product. Okay? That is something you need to address and kind of ponder. We'll talk about it in more detail when we get into lecture. I'm going to have to leave you hesitating on this last slide here, and I'll try and record a little bit more on what's going on with the reactivity of our carbon group later this weekend. Is there any reactivity of the carbon-hydrogen group? Hopefully you see no, but what if we bring it near another functional group? So in this instance, what I'm asking you to now evaluate is what chemistry is available in that bond. Okay? It's a tricky thought. Take some time to think about it. Maybe think about those famous 4 + 5 letter words that could be relevant for stabilizing a potential intermediate or product. And with that, I will leave you.